Okay, in this problem, well, in this video, I should say, we're going to do problem 553. So this is a angle of twist problem. It's nice because at least we have some torques going in opposite directions, so we have to be a little careful about the twist convention. So that's why I kind of chose this one. So it's pretty straightforward. It's fixed here at A, let's assume, so the angle of twist here is 0. There's a torque applied to D. That's a clockwise torque. And then at C, a counterclockwise torque, and then B, a clockwise torque. And first, just to show how we deal with the sign conventions, let's define an x-axis pointing down, okay? So around the x-axis, you can see D is actually a negative moment or torque. It's minus 30 in the x direction. C is a positive torque around the x-axis, so it's plus 20 in the x, and then the B is a minus 80 newton meters in the I direction. So, if you were to write these as vectors, right, this would be 30 newton meters minus on the I unit vector, right? This would be 20 newton meters around I, and this would be minus 80 newton meters around the I unit vector, okay? All right. So the way we're going to do this is we're going to figure out the angle of twist of D relative to A, and then C relative to D, and then B relative to C. Add all those up, and that'll give you the angle of twist of B relative to A. So the angle of twist of B with respect to A equals the angle of twist of D with respect to A plus the angle of twist of C with respect to D plus finally the angle of twist from B with respect to C. And why are we breaking up in those sections again? Because each one of these sections we have constant internal torque, we have constant cross-sectional area, J is constant, and G is constant. So we can use for each one of those, phi is the T L on J G. And if we have a problem where one of these things varies, we have to do the integration, right? We have to do the integral. All right, this is the general relationship, but if everything's constant, we can integrate it directly and get this relationship. All right. So let's do that. Let's draw the free body diagrams. So for each one of those, well, I think it says it's made out of steel, right? Yeah. So G for steel, just forget, G for steel is going to be 27 gigapascals. All right. And then okay, so let's get J. J is the same for all those. The diameter is 20 millimeters. So that's going to give me 1.57 times 10 to the minus 8th meters to the 4th. That's J. And then Well, the length varies for each section, right? These guys vary. And obviously the internal torque varies, all right? So, well, we can get the product JG. Let's do that because that appears in the bottom of everything. So J times G is going to be 27 times 10 to the 9th pascals times 1.57 times 10 to the minus 8th meters to the 4th. And that's going to give me 424.1, and that's going to be newtons per meter squared times meters to the fourth. So that's Newton meters squared. Okay? All right. So now let's get phi of D relative to A. So we need to get the torque in that section times its length, which is going to be 200 millimeters, divided by this JG quantity, right, which is the 424.1 Newton meters squared. All right? So we need to get the internal torque. So we do that from a free body diagram. So let's draw it. Let's do it this way. So let's draw the positive x direction going this way. So then, if we look at this, here's the cut here. We need to have the cut past D. So here's the point D, and then we also will have points at C and B as well. So at D, this is where we want to be careful of the sign convention. So at D, we have the negative, let me draw this bigger. So this is the x direction. Here's point B. Here's point C. Here's point D. And here's the internal reaction torque in section DA. All right. So this is on a negative face. So I drew it in the negative x direction. That's its positive sense on the negative face. Okay. So at point B, we have a minus torque. That's the minus 80, right? Or I should 80 in that direction, if you will. At point C, it's a 20. And then at point D, it's another minus. So it's minus 30. Those are all Newton meters. Okay, so the torque at DA, which is a minus, we're going to do sum of torques, or sum of moments, about the x-axis. Okay, so this is a negative moment, or negative torque. Then we have a minus 30 Newton meters. Then we have a plus 20 Newton meters, and then a minus 80 Newton meters. And that all has to go to 0. So that tells me that the torque, internal reaction torque in section D and A, D to A, or A to D, is going to be, we got a minus 10, minus 90 Newton meters, okay? Or in other words, it's actually acting on this face it's actually acting in this direction. Or if I were to cut it from the other section, it would be acting in that direction, okay? So again, the minus sign comes out here because this is the way I drew the arrow. The reason I drew the arrow is because this is the positive sense for an internal reaction torque because it's on a negative facing face. All right. So if I do that, then when I do this negative value into the twist angle, phi, all right, it's going to be negative 90 Newton meters times 0.2 meters over 424.1 Newton meters squared. Everything cancels out, and you can see you get dimensionless unit of radians. All right, I get a negative value here because I was careful of the signs, and that means that the rotation of D relative to A is going to be clockwise, because that's the negative sense. All right, so if I look down the x-axis is coming out at me. It's going to rotate this amount. Let me just get the numbers. 90. That comes out to be minus 4.244 times 10 to the minus second. Now that's radians, okay? So if we were to get that in degrees, that is times by 180 over pi. And that gives me minus 2.43 degrees. So it's the minus, so that means it's rotating. D rotates relative to A in a clockwise fashion. All right, so that's the first rotation. That's the rotation of D relative to A. So D rotates relative to A clockwise. Okay, now let's figure out, well, I can use the same free body diagram if you let me do it. So now we need to get the torque here. So we'll draw a section through CD. That'll give me the total torque in DC. Let me redraw that again. So again, here's the X direction. We have the 80 kilonewton, I'm sorry, 80 Newton meters acting at B. At C, we have the 20 Newton meters, that's point C. And then here, again, we assume positive because it's on it. Well, we assume going to the left, it's a negative phase, so it's positive in the outward direction. This is the torque in section D to C, all right? And so if we do sum of torques or sum of moments around the x-axis, that gives me minus torque DC plus 20 Newton meters minus 80 Newton meters goes to 0, or that gives me that the torque in DC is equal to minus 60 Newton meters. All right, so again, it's acting actually in the positive X direction, okay, on this face. All right. So if I were just to make it clear again, it's just like flipping the signs on the internal axial forces, right? So this would actually act in this direction on that face. Or if I looked at the section from the left side, right, it would act this way. Right? It's actually acting in that direction, okay? But we're going to keep this sign convention, so that's what it is. So again, now we can get the phi of section C relative to D. That's the torque at DC, the length of section DC over the JG for section DC, but that's the same as all the other ones. So that's minus 60 Newton meters times the length, which is 600 millimeters or 0.6 meters. And then JG is 424.1 Newton meters squared. And this gives me 8.49 radians, which is equal to minus 4.86 degrees. Okay? So again, let's try to draw it. If this is the x-axis, and this is point D, and this is point C, then this is actually rotating in a clockwise sense by this 4.86 degrees. And this is times 10 to the minus second. Why didn't I? Sorry. Okay. All right. Now we need to get the rotation of C relative to B. That's going to be the torque in section, or I should say B relative to C. That's the torque in section BC times the length of CB over JG. So now to get the torque in section CB, we'll take a cut there. We have just the 80 kilonewtons acting in that direction. Sorry, 80 Newton meters. I keep calling it kilonewtons. Again, we assume positive outward. So that's the torque CB. Okay, then we do sum of forces. What you get is minus torque CB minus 80 Newton meters equals 0, or that the torque at CB is equal to minus 80 Newton meters. Okay? So again, we have a minus sign here, so the twist is also going to be minus. All right? So now the twist of B relative to C is the minus 80 Newton meters. The length is 0.8 meters. And then the JG is the 424.1 Newton meters squared. And so that gives me 80.8 times 424.1 divide. Did I do that right? It seems off. 80.8 times 424.1 divided. Yep, okay. That's 0.151 negative radians, which is equal to minus 8.65 degrees. So again, this is also counterclockwise. So all the twists are counterclockwise, okay? So you have to be careful about the sign. So even though this torque flips direction, right? That doesn't mean that this section is going to rotate necessarily in the same direction as the applied torque, because the rotation sense depends upon what is the sign of the internal torque, not what's the external applied torque. So each one of these sections is going to rotate. This is going to rotate clockwise, this is going to rotate clockwise, and this is also going to rotate clockwise. Okay. So now when we add those all up, the phi of B relative to A is the phi AD plus phi DC plus phi BC. And that's going to equal, my numbers, let's do it in degrees, minus 2.43 minus 4.86 minus 8.65. And that gives me a total of 15.9 with a negative degrees. Or in other words, 15.9 degrees clockwise. Okay?